Now I arrive. Now I arrive. So the simplest case is the complexity index, simplest class is complexity index 0k. Now, let us consider the complexity class 1k with the same meaning. It means that the sequence omega n satisfies now this equation with n equal to 1. So I must have the second difference derivative of omega n is equal to 0. And you know from the standard books on finite difference equation that this equation has a unique solution depending on two parameters. Of course, this must be subjected to the to the condition that they must be greater or equal than 0. In lower order is a simple inequality. You see, this means that intuitively the second derivative is 0, so this goes like x. But x is discrete, so it goes like n. Okay? So now you recognize when you have the parameters b equal to 0 and a equal to 1, you have the standard Gaussian. See? But what is very interesting is that even for analysts, this should be a challenge. Because what happens if b is different from 0? You see, to put b different from 0, simply add a parameter to the Jacobi. So, the only constraint is positivity. But you know, this is a condition of Jacobi sequence. And the Jacobi sequence is very nonlinearly related to the measure. How? We don't know anything about this measure. Have they all measure a density? We really don't know. There should be some criterion. I hope that we will find that from the Jacobi coefficients tells you information on the fact that the measure has a density or not. Okay? I don't know such theorems. Probably the only known is this theorem of Stieltjes inversion formula that I mentioned to you. But this is the only general result that I know. And we have already studied, we have already seen that when, however, you see the additional parameter, they change the measure very much, but it doesn't change the difference because it's constant. In that formula, b is constant, so it doesn't change the difference. So the commutation relations are all the same, and so the Fock space will be the same, which is the standard Fock space. One more standard Fock space on 1 degree of freedom. Okay? So this is a standard Gaussian. Now let us see the next step. The next step is complexity index 2k. Another open question. We are for b different from 0. What happens? But here, the standard Gaussian, we have also taken k equal to 0. Okay? Because the standard Gaussian is Bn, and n starts from 1. But what happens from where k is strictly greater than 0? Intuitively, these measures should be very near to the Gaussian, because they differ from the Gaussian only for the fact that just a moment. Yes, only for the fact that the first k plus 1 coefficients are arbitrary. Then the Gaussian sequence begins. The Gaussian Jacobi sequence, which is a multiple of n plus b, but forget b, okay? So intuitively they are very near to the Gaussian. So nearer as k is smaller. For example, k equal 1. If only the first differs, what happens?
Is there an atom?
We don't know. There is no answer. No answer. This is why I say it's a very interesting field, because it poses problem to many branches of mathematics, but to analysts, very many problems. Because these are non-trivial problems that, however, I'm sure they can be solved. One should develop techniques or dig into the old analysis and find some technique which allow to solve this problem. The case 2k, a similar problem arises. In the case 2k, it means you have an equation of third order, a difference equation of third order, starting from a certain point k. And from the general theory of difference, the difference operators, you know that the solution of this equation depends on 3 parameters, because you have a n square plus b n plus c. In probability theory, such a sequence came out in 1939 from a completely different direction, nothing to do with Lie algebra, but with the famous paper of Meixner that I mentioned several times, which is a very nice, interesting paper. But it had to do with the generating functions of orthogonal polynomial of a very special holomorphic structure. So again, also the bridge with the theory of complex variables is coming from the Meixner paper, okay? So this sequence was very well known. It exactly characterizes Meixner classes. And now, what is the Lie algebra? What is the Lie algebra? Well, let us do the calculation so we have to calculate now this will give the square and then you have so the C doesn't bring any contribution. Here we get the contribution B, and here we get the contribution 2an plus a, which will be included in the constant. So if you in the language of our commutation relation, we have that d omega lambda is 2a lambda plus a certain constant c. But this is exactly the SL2R relation, because we have A minus A plus equal, let us say, twice A lambda plus C. Remember, this is the D omega lambda. And then you have a standard commutation relation. A minus lambda equal sorry this this A is not, this is bad language. Put another letter, how we say that this is a C0 and C1.
This A is a bad notation because it confuses with annihilator.
So, you see, now you have the constant means a central element, identity morally, but in Lie algebra language is central element. So this is a central extension of SL2. Because SL2R is given by the commutation relation you can call this whole operator, you call M, and adding a constant will not change. Of course, you rescale, you have to rescale a little bit, because C1 you must absorb into the AA DAGA by dividing by the square root, and you have to normalize. But with simple normalization, you see that this differs from this. In this case, the central extension is a known theorem that all central extensions of SL2R are trivial. So it means there is no non-trivial cosigners. So you can absorb this into the definition and you find this commutation. But for constructive purposes and application to quantum mechanics, this constant C is very important. And this comes, we found many years before knowing this theory of orthogonal polynomial, and this constant C came from physics, and it is interpreted as a renormalization constant, which plays a very important role. Otherwise, your presentation will be trivial.
So the C0 is the
Is the renormalization constant. It's a non-trivial renormalization. It's a new proposal. From that came our idea of quadratic. This algebra, we call it renormalized square of y naught. This is SL2R. This is the algebra SL2R. And this we call the renormalized square of white noise. Because it came out, only a posteriori it was recognized. This was a remark by Uwe Franz, and also by Partasarati, we had a correspondence, that I say, look, but this is SL2R. Originally we didn't recognize. We simply deduced this commutation relation. You can deduce by yourself. In the case of one dimension, the renormalization is needed when you go to the field theory. But if you do the one-dimensional case, this algebra is exactly the algebra which is satisfied by number operator. You take 1 degree of freedom standard boson, and A plus A minus are standard boson created and annihilation. And then you take the squares. And if you compute the commutations, you find this. And the lambda, of course, lambda, in the Gaussian case, lambda is a daga A. There is a direct bridge between the two. Okay. So, well, I should, I essentially said what I did. So, starting from index 0, 3, 3 on, n equal 3, so this is 2. By the way, also here, we know for k equal to 0. But what happens for k different from 0? We don't know. The Meister bridge is with k equal to 0, capital K equal to 0. So is the complexity index 2, 0. But what if we want to k for k not 0? And for n equal to 3, n greater or equal 3, then L 0 of x is infinite dimension. So I said I wanted to show you this, as you see, is a very outline, but there is some interest because you have now very natural algebraic classification of measures, of probability measures. You go from the simplest, which has information complexity lowest, to the highest. But even in the lowest, we know very little. You see? Moreover, all the Lie algebra that come out, with the exception of the first two, the gap. I proved that this was in a paper with Lu and Barumi and Reimann, that in the case of index 0k, for every k, the Lie algebra is the algebra of all matrices, so not very interesting. All my finite dimensional, k times k. So, not very interesting. For n index 1k, we know the Lie algebra is, because Lie algebra is independent of k, depends only on n, is Heisenberg algebra. For n equal to 2, we know it is SL2R, and from n equal to 3, we know only that it is infinite, greater or equal to 3. We only know that it is infinite dimension. But this is a very interesting family of new Lie algebras, which are, in my opinion, worth to study. And think that now we are, why I call L0 this algebra? Because L0 doesn't contain the A0 operator. But if we put the A0 operator, we have a larger algebra which I call LX, because it contains more objects. So it depends on both Jacobi sequences. You see, All these are very interesting to study.
What is L0?
L0 is the one generated, L0 is the linear span, the Lie span. Lie span in the sense of Lie brackets. And Lx is the Lie span of a plus A0.
A0.
Well, zero is a subalgebra. But the algebra, full algebra canonically associated to the probability measure is this. Because the two sequences uniquely fix the state on the polynomial algebra. But the first algebra only characterizes the symmetric equivalence class. And what will be the dream to conclude is dimension d greater than 1. This is completely open. Of course there are Lie algebras, but there the problem of canonical form that I mentioned many times, but we had no time to go deeper, will enter. And we must do like in geometry. Like in geometry they classify manifolds. We have to classify the commutation relation associated to probability measures. Then we will have a deeper understanding